Right, let's get started. Yeah. Right, so everyone, this is SeungryongKim. So today we will finish the matrix factorization, especially Elliptic factorization. So it was selection of the 6, right? It was selection of the 6, and yeah, let's recap. Before that, here, okay. One more notification is that we have a midterm exam, right? Midterm exam on April 28th, so from 5 p.m. to 7 p.m. Location is Aggie Nungston Center 301 and 302. We will let you know your room number. Anyway, so this is going to be an offline exam. So you are allowed to bring your own A4 size cheating sheet, both sides, but any electronic devices are not allowed. Please bring your student card to check your attendance. Okay, right. Okay, so last week we started the matrix factorization, right? What was the it was the chapter 2.5. What was factorization? Factorization of the matrix A is an equation that expresses the matrix A as a product of two or more matrices like this, like this. A can be factorized to the two matrices B and C. So why we have to know that? So Elliptic factorization is motivated by the common industrial or business problem of solving the sequence of the equation x equals b1 or b2 or b3. So when A is immutable, one could compute A inverse and then compute A inverse b1, inverse b2, something like this. But it's going to be the inefficient way to solve each equation. So Elliptic factorization can be the efficient way to solve your linear system. So one of the assumptions in elliptic factorization is that matrix A is an n by n matrix that can be low reduced to the echelon form without low interchanges, which will be generalized later, but we just assume matrix A can be low reduced by replacement or scaling low the low operation, right? Elementary operation. Then elliptic factorization can be written as L and U. L is the m by m matrix. M by m matrix. You need lower triangle with a 1 on the diagonal, looks like this. And U is the m by n echelon form of the matrix A. M by n. So we already know this U is a echelon form. Echelon form. So the elliptic factorization is highly related to the matrix low reduction. Okay, so we'll talk about this one later. Before that, why elliptic factorization is the efficient way to solve your linear system x equals b, because due to the thanks to the efficient matrix form like this and this. Lower triangle and upper triangle. So anyway, so when we decompose matrix A to the LU, then AX equals B can be factorized to the two kinds of problem, Ly is equal to B, and then UX is equal to Y. Then first solve Ly equals to B for Y, then solve UX is equal to Y for the X. So, and we can see example why LU factorization is the efficient way to solve your linear system. So first of all, okay, if we already know L and U of this matrix A, L and U, then first of all, Ly is equal to B is our first linear system. So how to solve this? Looks like this. Then first of all, to solve this linear system, we have to further low reduce this LP matrix to the REF form to get to get the vector y as a solution. So in this procedure, we can see there are 6 addition and 6 multiplication here. 그렇죠? Similarly, and then we have to find the solution for the ux is equal to y, which is the exactly similar procedure to the backward page of the rule reduction algorithm. So as you can see here, which requires 4 division and 6 multiplication and 6 addition. So finally, to find out x and the solution x, we require 28 arithmetic operation or pull-ups, excluding the cost of the finding L and U. In contrast, the row reduction of the A, B to the IX, just to solve the A equals B, takes 62 arithmetic operation. Even though we fully require additional complexity to decompose your matrix A to the L and U. So that's why we have to know the LU factorization. Anyway, how to LU factorize your matrix A? To understand this, we have to know elementary matrices, replacement, and scaling. 그렇죠? So we also discussed the inverse matrix of the replacement matrix or the scaling matrix. Then we see the example. Matrix A looks like this and E looks like this. So first of all, this matrix 1 0 3 0 1 0 0 0 1 is a replacement operation that can replace original R3 row by previous R3 plus 3 R1. Right? Similarly, inverse of this matrix can be the 1 0 -3 0 1 0 0 0 1 due to the by definition here. We did not prove this one, but we can easily prove this one is correct because we can just compute E times E inverse, or E inverse times E is going to be the identity matrix. So this is the correct inverse matrix. Anyway, we will use this one to derive LU factorization. And one more thing is that if we sequentially apply elementary matrix E1, E2, and E3, then, for example, this one, and this one, this matrix is going to be the 2, 3, 4 here, right? And the inverse of this matrix can be blah, 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 and looks like this, right? So this is the properties of replacement, okay? So we will use this one to factorize your matrix in a LU factorization manner. Right. So this is the last week. Any questions so far? 자, 우리 뭐 한 번 더 얘기를 하면 뭐 LU factorization 이제 오늘 마무리할 건데 LU factorization에서 대해서 우리 이제 얘기를 했었고요. 그렇죠? LU factorization 하면 왜 더 빠른지에 대해서 얘기를 했었고 결국에 매트릭스 L과 매트릭스 U가 갖는 특성 때문에 정말 빠르게 ly equals b와 ux equals y를 정말 빠르게 풀 수 있기 때문이었고 그냥 어떤 arbitrary matrix A에 대해서 x equals b를 푸는 것보다 훨씬 빨랐기 때문이었던 거고 결국에 LU만 잘 팩토라이즈 할 수 있으면 우리가 이제 이런 것들 할 수 있다라는 거였고 결국에 LU가 무엇이냐? U가 결국에 에실론 폼이니 에실론 폼을 만들어가는 과정이 어떤 sequence of elementary operation, elementary matrix일 거기 때문에 그런 elementary matrix를 잘 고려하면 L이라고 하는 펑션을 만들 수 있지 않을까? L이라고 하는 매트릭스를 만들 수 있지 않을까가 저번 시간까지 우리가 했던 얘기들이었죠. 그렇죠? Any question? Any question? No? Right? Right. So here. Yeah. So again, the assumption in LU factorization is that matrix A is a n by n matrix that can be low reduced to the echelon form without low interchanges. So this assumption allows us to low reduce matrix A to the echelon form using echelon form U using only row replacement that add multiple one row to another row below. So just by composition of the row, composition of elementary matrix for the row replacement. So in other words, if you have matrix A, and we already know matrix A to row reduced to the echelon form, then there are several kinds of elementary row operation, especially row interchanges. Then this one can build matrix L. That is our target, right? Then by using this one and this one, A can be factorized by L and U. Okay. So why these kinds of things happen? First of all, we already know if matrix A is row reduced to the matrix U, there exists elementary matrices E1, E2, and EP, which is elementary matrix for the interchange. Then in other word, there exists unit lower triangle elementary matrix looks like this, which is form of here. So, this one. Let's suppose that there are P kinds of elementary matrix that can row reduce original matrix A to the U. Then we already know matrix A can be the inverse of E1, E2, E3, blah blah blah, EP times U. Then we can assume this one has L. This one is L. Where LU, where L is defined like inverse of the E1, E2, EP. Right? In this case, we can achieve L and U for two factorized original matrix A. This is our observation. So first of all, composition of the elementary matrix or inverse of them looks like this. Row triangle with one on diagonal here or here. Then it's kind of form for the L, right? Key observation is that, again, product of row triangle elementary matrices E1, E2, EP, which is the blah blah blah, looks like this, is also row triangle. 그렇죠? Is also triangle. This inverse of this product L is equal to inverse of the E1, E2, EP is also row triangle, right? Then this is our target. Then here, let's suppose that this is the equation 3 and this is equation 4. Then row operation in 3, which reduced A to the U, also reduce L in 4 to the I. L. The row operation in 3, which reduce A to the U, also reduce L to I. Here, 그렇죠? L to I. L to I. Right. Then, what does it mean? By just multiply this one, 그렇죠? Here and here, then it's going to be the identity, 그렇죠? This one, L to the I. Because here, because 그렇죠? Here, 그렇죠? This sequence of the elementary operation times L is going to be the I. So this observation is key to the construct L. Then here's the algorithm for the elliptic factorization. It's very simple. First of all, reduce A, matrix A, to the echelon form U by a sequence of row replacement operation, if possible. If matrix A is not row reduced to the echelon form. I mean, if we can't row reduce matrix A to the echelon form U by sequence of the row replacement operations only, we can't use the Elliptic factorization, right? So we just assume that row replacement operation is all you need to compute two row reduced echelon form. And then place entries in L such that same sequence of row operation reduce L to I. So in other words, let's suppose the sequence of row operation is E1 blah blah EP. Then place entry in L such that sequence of the row operation reduce L to I. Then in other words, L is equal to inverse of E1 EP. This is our target matrix L. Target matrix L. Any question? 자, 질문? 여기까지 클리어하죠? 그쵸? 클리어하죠? Right? So, let me show you example. Step 1 is not always possible when it is the argument above show the factorization exists, right? So, when it's not always possible, if matrix A requires the interchange for the row reduction, right? Then it's not possible. But when it is argument above shows the factorization exists. By construct L will satisfy here, 그쵸? Using the same E1, E2, EP in equation 3, 그쵸? Here, 그쵸? Then L is invertible, 그쵸? L is invertible. Why? By inverter matrix theorem, 그쵸? Because the L is the sequence of the elementary matrix, so it's invertible, 그쵸? Why? The multiplication of the invertible matrix, 그쵸? Each elementary matrix are invertible, right? So L is also invertible with inverse of the E1, E2, EP is the inverse of the L. In other words, L inverse times A is equal to U, 그쵸? L inverse times A equal to U. In other words, A is equal to L. So step 2 will produce the acceptable L. This is just to explain that we discussed so far, right? Then, in other words, here, let me show here. Then L looks like this is our target L, and pi product U 그 echelon form of U, echelon form of the matrix A is called matrix U. Then we can factorize original matrix A to the L and U. This is my Elliptic factorization algorithm. Right. Any question? No? Okay. So today I will show you some example for the Elliptic factorization. So original matrix A is 4 by 5, 그쵸? 4 by 5 matrix. Then, so we want to factorize A is equal to L and U. So first of all, what is size of L in this case? 자, what is size of L in this case? 뭐죠? First question. Size of L or size of U in this case? Anyone? 자, when A is equal to size of the A is 4 by 5. Then what is size of L? L 4 by 4, 4 by 5. Right. So, right. L is rectangle 4 by 4. U is 4 by 5 matrix. So, right. Then let's find out L and U. L and U. So, first of all, to factorize LU, which was the algorithm, first of all, row reduce A to the echelon form. And let's do that. Step 1, which is step 1, right? So, what is our first strategy? To make this term, third term as 0. Then let's do that. So, new R2 should be plus 2R1 to make this term as 0, right? This term, R3 should be previous R3 minus R1, right? R1 to make this one 0. And R4 should be R4 plus 3 times R1. 3 times R1. So it's going to be 0. Then let's think about shape of the E1, E2, and E3. E1, E2, and E3. So first of all, if this E1 is charge of this replacement, what is some original? What is some matrix? Which matrix can make this replacement? Maybe it's going to be 0, 0, 0, and maybe E1 is 4 by 4 matrix, right? Then which matrix can fill this replacement? R2 plus 2R1. which matrix? 뭐죠? 어떤 매트릭스가 첫 번째 요 리플레이스먼트를 대체할 수 있다고 했죠? Anyone? 자, let's go back. This one, right? So, this K means, 그쵸? Here, I to J였어. I's row and J's column should be K, not a 0, right? Then, in this case, maybe 2 plus 2 should be right? So R2 should be 2, 1, 0, 0, right? And remaining part should be 0. All the up diagonal part and other part except for this position, right? What about this E2 for this replacement operation? This is 1, 1, 1, 1, and 누가 할까요? 우진? Again? What is that? Right. -1, -1, 0, 0. Looks like this. Right? 0 and 0. 다시 써볼까요? 1, 1, 1, 1, -1, 1, 1, 1, 1, 2. E2 is already still 4 by 4. E3 may be 4 by 4, right? And E4 should be 1, 1, 1, 1. Similarly 1, 3 here. So right here, right? Then let's say this is the new E, matrix E, which is E3 times E2 times E1. Then matrix E is going to be 1, 1, 1, 1 on diagonal, and 2, -1, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? This is E. To row reduce matrix A to this matrix, right? Then what next? We have to row reduce some matrix here, right? Then let's do that. Okay. Then for this new matrix, we have to multiply further elementary matrices. 그쵸? Then let's do that. Then first of all, how can you make this term and this term as 0? Then my new R3, previous R3 plus 3 R2 or R4 minus 4 R2, right? Then our E4, let me use the black color. F4 is going to be 1, 1, 1, and 3 here. You mean part of 0 looks like this. And E4, E5 for this replacement operation is going to be 1, 1, 1, 1, negative 4. 그쵸? Negative 4. Right. Then let's say this new matrix E is E5 times E4, which is what? 1, 1, 1, 1, 3, negative 4, 0, 0, 0, 0, 0. Right? Right. Then we achieve this matrix. In other words, if we multiply this matrix to the matrix A, original matrix A, then we achieve this matrix, right? Okay, let's further reduce this one. Then finally, we have to make this term as 0. Then R4, new R4 should be original R4 minus 2R3, 2R3. So this new E6 is going to be 1, 1, 1, 1, negative 2, 0, 0, 0, 0, 0, 0, right? Looks like this, right? So this is echelon form, right? Echelon form matrix A. Then let's say this is matrix U. Matrix U. In other words, matrix A is further reduced to the echelon form U by using this matrix. 그쵸? By this matrix. 그쵸? Thanks to the properties of the matrix multiplication, this equation can be written as, okay, looks like this. 그쵸? E6, 5, 4, 3, 2, 1 times A is equal to U, right? And we already know this one is invertible, right? Then let's multiply inverse of this matrix to left hand side, right hand side, and left hand side is going to be the A, original matrix A, and this is going to be the inverse of the blah blah blah, right? Times U, right? And we already know this one is going to be the E1 negative 1, E2 negative 1, E3 negative 1, E4 negative 1, E5 negative 1, E6 negative 1. E6 negative 1. Again, this one is inverse of 1, 1, 1, 1, 2, negative 1, 3, 3, negative 4, negative 2, 0, 0, 0, 0, 0, 0, here. By multiplying this matrix, 그쵸? Here, this one, this one, this one, this one, this one, this one, right? Then final matrix E, it's going to be, looks like this. And inverse of this matrix is, we already know, right? 1, 1, 1, 1, negative 2, 1, negative 3, negative 3, 4, 2, 0, 0, 0, 0. Right? Then this is matrix U. This is matrix U. Right. Then, again, what was the original matrix A? So, what was the original matrix A? Here. So, 2, negative 4, 2, 2, negative 4, 2, negative 6, 4, negative 5, negative 5, 0, negative 1, 3, negative 4, 7, 5, negative 8, 1, negative 3, negative 2, 1, 8, 1, which can be further low reduced. 1, 1, 1, 1, negative 2, 1, 3, negative 3, 4, 2, 0, 0, 0, 0, 0, 0 times matrix U, and matrix U was here. So U was here, and where is that? Yeah, 2, 4, negative 1, 5, negative 2, 0, 0, 0, 3, 0, 0, 1, 0, 0, 2, 2, 0, negative 3, 1, 5. This is matrix U, and this is matrix L and matrix U. L and U from matrix original matrix A. This is the Elliptic factorization algorithm, right? It's very easy. So it's very, very straightforward, but it's a very efficient way to solve your linear system, right? Then you can solve your linear system by using this kind of technique, 그렇죠? This kind of technique, because you already know how to factorize your matrix A, 그렇죠? In a Elliptic factorization algorithm, 그렇죠? That's it. Any question so far? Any question? 없죠? No? No? Clear? It's very important because you have to take a midterm exam next week, right? So it's very important. Midterm exam will contain one of the problems that require high level understanding of the Elliptic factorization. Maybe you have to factorize your arbitrary matrix A. So it's very, very important. Nope. Okay. So this is the full procedure to Elliptic factorize your matrix A, and there are more efficient way, more systemic way to for Elliptic factorization. So the idea is like that. Okay. Here's matrix A. Then we want to low reduce original matrix A to the matrix U. Looks like this. You already know how to low reduce this original matrix A by using interchanges from looks like this here. So then in a systemical manner, highlight entries in each matrix that are used to determine sequence of the operation that transform A onto U. So what does it mean? To low reduce original matrix A, first of all, we have to consider here in the first step, right? And after that, we have to consider this term, 그렇죠? And then we have to further consider this term and this term, right? Why you have to consider this column when you low reduce original matrix A? Because they are pivot column. Right? It's very straightforward, right? Then, and we will use these properties. The highlighted entry above here, so here, determine low reduction of A and U. At each pivot position, at each pivot column, divide the highlighted entry by pivot. Divide highlighted entries by pivot. Place the result onto L. What does it mean? Okay, here are 4 kinds of pivot column. 그렇죠? Then divide highlight the entry by pivot and place the lizard onto L. So first of all, this column, and here's a pivot. Then divide by 2 the values on the pivot position. Then this column is going to be 1, negative 2, 1, negative 3. Okay, this one should be divided by 3. It's going to be a new column. This one is going to be 2. It's going to be a new column. Negative divided by 5. Then this kind of column, it's going to be L. It's going to be L. It's very, very easy. So it's a systematic way, and you can easily use this one. But you have to understand why this kind of simple division can build this matrix L, because of this kind of procedure. Okay, this kind of procedure. Right. So in other words, how to solve the LU factorization? First of all, row reduce modular matrix A to U and check the pivot columns at each step. Then just build the matrix L, which is going to be our final matrix L. Right? This is LU factorization. Any question? Question? 자, 한국말로 한번 더 설명할게요. 그래서 뭐 너무 쉽죠. 그래서 뭐 LU factorization은 결국에 시스테믹하게 풀면 이렇게 풀면 돼요. 기계적으로 뭐예요? 결국에 U라고 하는 걸 로리두스하는 이런 중간 과정의 매트릭스들이 있었을 거고, 거기에서 피벗 컬럼들이 있었을 거고, 그 피벗 컬럼들에서의 피벗 포지션, 가장 위에 있는 점이죠. 가장 피벗 포지션으로 나눠준 값, 나눠준 벡터들 이렇게 되겠죠. 이것들을 그냥 해당하는 위치에 순서를 쌓기만 하면 그게 매트릭스 L이 된다. 그냥 이게 결국 시스템 웨이예요. 왜 그러느냐? 이런 과정들을 잘 보면 결국에 그렇게 되더라. 왜 그러느냐? 이런 거죠. 결국에 우리가 이 매트릭스를 찾아내는 거, 결국에 이 컬럼들에 어떤 밸류가 있었느냐. 이 매트릭스 결국에 프리비어스죠. 그렇죠? 이 컬럼들에 어떤 밸류가 있었느냐. 또는 이 매트릭스는 결국에 이 컬럼들에 어떤 밸류가 있었느냐에 연관이 되기 때문인 거죠. 그렇죠? 그렇죠. 그렇게 되는 거죠. 그래서 이렇게 시스템을 풀려면 이런 식으로 풀려면 LU factorization이 된다 라는 거죠. Any question? No? No? Right. And so far, we just assume our matrix A requires row reduction algorithm, row interchange only for the to row reduce to the echelon form. But in practical world, row interchanges are nearly always needed. So, because partial pivoting is used for the higher person. For example. So okay, let's go back. What was the partial pivoting? What was the partial pivoting in your row reduction algorithm? 자, 우리가 row reduction algorithm 처음 배울 때 partial pivoting 뭐였죠? 자, partial pivoting. What was that? What was the partial pivoting? Looks like this. If your matrix was 0, blah, 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 and let me say 3 looks like this, then you have to interchange last row with first row can make the largest magnitude of the value should be pivot position. For the computation efficiency, it was the partial pivoting, right? So to derive partial pivoting, you require the row interchange, right? Anyway, in many cases, low interchanges are needed, but the Elliptic factorization discussed part cannot be used in this case, right? Because we already we just assume we only require replacement operation, right? Then we need further technique. So then we will introduce some more advanced one, permutated Elliptic factorization. Permutated factorization. What does it mean? Looks like this. If we already know what kinds of low interchanges can be used, then we can formulate this low interchange by matrix P. Matrix P. Matrix P, which can interchange each row. Right? So how can we build this permutation matrix P? By using this one. Looks like this. This matrix can be permutation matrix. Can be used for the permutation, right? Because it enables or interchange each row. Then first of all, we permute original matrix A first, and then factorize this one to the LU. Factorize this one LU. Why? This matrix no longer requires row interchange, but PA matrix, let's say this is new matrix A prime, requires only replacement operation only for the low reduction algorithm. Then we can we can factorize PA matrix, let's say A prime to the LU. Then solving with the permutated LU factorization. Then how? Okay, so our original linear system was AX equals B. Then first of all, we multiply permutation matrix P to left-hand side and right-hand side. Then if we low reduce, we factorize PA to the LU, then it's going to be LUX times LUX is equal to PB. Then let's follow the previous work. Write Y for UX. Looks like this. Then find X by solving pair of equation. First of all, LY is equal to PB, not a P anymore, PB. So let's assume that we already know the permutation matrix P. Then first equation is going to be LY is equal to PB. Then next equation is going to be UX equal to Y. UX equal to Y. Second equation. Then this is LU factorization algorithm for the general cases, general matrix cases, right? That's it. Question. Clear? This is the end of the LU factorization. Thursday we will move to the another topic. So if you have a question, please let me know now. 자, LU factorization 어렵지 않죠, 생각보다? 뭔가 거의 개념적인 얘기보다는 결국에 어떤 프랙티컬한 솔빙 테크닉들이었고요. 어렵지 않았을 건데 질문. No? 시험 범위? So the question was the midterm, how much midterm cover, right? Maybe. Okay, Thursday we will start the lecture note 7, 그렇죠? Maybe midterm exam will cover lecture note 7, right? So because before midterm exam we have 2 more class, right? This Thursday and next Tuesday, right? Maybe we will cover by lecture note 7, but let's see. Okay. Any questions so far? Nope. Alright. What time? 5:45. I'd like to start lecture 7, but okay, 30. Maybe I think it's enough. I think it's enough because we have a 2 more class. So I think we can stop here today. So finally, last question. 자, 오늘 여기까지 될 것 같아. 네, 오늘 좀 빨리 끝났는데 여러분들이 너무 잘 따라오셔서 금방 끝났고 이제 목요일 날 우리 렉처 7 시작할 거고요. 아마 렉처 7까지 시험 범위 할 것 같긴 한데 봐야 될 것 같아요. 어디까지 나갈지. 네. Do any practice exam? What do you mean by practice exam? Practice exam? You mean the pre-test? Maybe some of you already have our previous, I mean the last semester's problem sheet, maybe. Okay. I think I can share previous problem sheet if possible. Okay, I'll let you know Thursday. But yes, yeah, I will let you know Thursday. Any other question? All right. So if not, let's finish only today. And Thursday we will start lecture 7, lecture 7, which is very, very important concept, subspace length or something like this, right? No? Any question? No? Okay. All right. So that's it. So this is end of today's lecture, and this is end of matrix factorization, especially Elliptic factorization. Thank you very much, and see you Thursday. Okay? 자, 여러분 오늘 뭐 여기까지 합시다. 일찍 끝난 것 같으니까 여기까지 하고요. 우리 목요일 날 이제 팩토라이제이션 다음에 이제는 우리가 서브스페이스 랭크 개념들을 좀 배울 건데요. 보고 우리가 시험으로 들어가도록 합시다. 그렇죠? 오케이, 여러분 고생하셨고요. 목요일 날 봅시다.